Hi, hello, and good day to everyone. Today, I'm to present about the maneuvering project for the dynamic of marine structure. My name is Arvinthan, son of Thiagarajan, and my group members are Nick Mohammad Hafidz, Tasfiqul Islam, Haifaa Zira, Wan Elmi, and Norsyaqim Iqbal. The content of our project is introduction, ship simulation software, maneuvering, performance in the Swiss Canal, result and discussion, conclusion and reference. Now we're going to see about the introduction part. So introduction part, mainly we are going to focus about the maritime maneuvering standard development. These developments are to ensure the ship safety and operational effectiveness. It also adapted to the vessel complexity size of the vessel and criteria of the navigation capabilities. Also, national regulation addressed the ship maneuverability in the early 20th centuries. The international efforts to standardize the measures begin in the mid 20th centuries with the IMO formation in 1958. Next, we're going to see about the IMO role in the ship performance assessment. Established the subcommittee on the ship design and equipment in 1960 and the 1970, adopted the international conservation for the safety of life at sea, SOLAS, in 1960s. And then also it adopted the specific maneuverability criteria in 1990s. It also aimed to ensure the safe navigation and the essential maneuvering contributing to the maritime safety efficiency. Next, we're going to see about the turning circle maneuverability overview. The test vessel's direction change through the 360-degree turn. The measures advance and transfer the tactical diameters and the final diameters are calculated. Ensure the IMO's criteria, tactical diameter should be not exceed the 5 times of the ship length overall, LOA. Overall length of overall assessment. The final diameter should be proportional to the ship size and so ensure the safe navigation and essential maneuvers. Zigzag maneuver overview. Next, the test response to the rapid radar changes. And then the crucial for the controlling sudden course alteration. The standard 10 degree or 10 degree and 10 degree zigzag alternatives for the rudder angles. The measure the first and second overshoots angles and the yaw checking availability. IM also mediates the first overshoot angle within the 10 degrees for the ship and next 10 degrees for the with the 10 degree of the rudder angle. This is from my side. My friend will be continuing. Thank you.
My name is Nick Mohammad Afif. I'm going to present about the ship simulation program. The maneuvering simulation programs were developed by UTM researchers in order to apply the mathematical equation and simulate the mathematical model for the maneuvering performance evaluation. The programs are divided into three different programs for deep water, shallow water, and restricted water. The example for deep water model is as shown in the figure. The model consists of hull module, propeller module, and rudder module that apply the mathematical equation and simulate the maneuvering performance. Typically, this model can simulate the vessel performance for turning circle and zigzag. Two different vessels, as specified in the table below, has been selected for this project to study the effect of ship size and vessel speed on the maneuvering performance in accordance with the IMO criteria. Ship parameters, as shown in the figure, contain several inputs for the model, such as ship particulars and hydrodynamic coefficient of hull, propeller, and rudder. In order to investigate the performance of the container ship and LNG carrier, the author has opted to run the vessel at vessel speed of 8 knots and 6 knots. The result of simulation for both turning circle and zigzag test are discussed in the fourth section of this presentation. This is example of turning circle for a large container ship at 8 knots in deep water. Basically, we can determine the advanced and tactical diameter from the simulation. While this result is for simulation of 10-degree zigzag test, we can measure the first overshoot and second overshoot from the result. This is result for simulation of 20-degree zigzag test. We can measure the first overshoot from the result as required by the IMO.
Assalamu alaikum. Now I am going to present for the maneuvering project. My name is Tasfiqul Islam, and I am going to present for the ship simulation shallow water case. First of all, we are going to check the turning circle maneuverability in a shallow water. So initially a predefined simulate model has been run accordingly to simulate the trajectory of large container ship. Then input parameters are set for two different vessel speed, that is one for 8 knots and another for 6 knots. After that we get the output results. That means we get first calculate the advance and then we calculate the tactical diameter, which will going to show in the result and discussion section. And for the other vessel, that is the LNG tanker, these procedures has also been applied accordingly. So that is the basic steps for the turning circle maneuverability. Then for zigzag maneuvering test, first of all we are going to check the 20-degree. So initially a predefined simulink model has been run accordingly to simulate heading and rudder angle. Then from the output we get the first overshoot angle. Then the same methodology has been also implied onto the LNG tanker vessel. So here in this case only first overshoot angle will be calculated. Now for 10-degree zigzag maneuvering test, both first and second overshoot angle will be calculated. And like the 20-degree maneuvering test, the procedures will be the same. Also the input parameters for two vessel scenarios, that means the two speed in the two speed scenarios has been depicted in further section. And then the measured parametric values of advance, tactical diameter, first overshoot angle and second overshoot angle have been further investigated, which will be shown in the result and discussion section. Now this is our simulink model for turning cycle maneuverability. So here in this case we just open the gate for this line to turn on the turning cycle maneuverability and get the result from the XY graph here. Then this is the figure for zigzag test. For zigzag test, the gate opening will be like this, and we have to just change the parameter to 20 and for 10 to accordingly for the two test, and we get the results from this scope here. Now the input that has been given for the code to run or simulate is shown here in these two figures. First of all, this is the parameters for large container ship, So it has been shown here that the length here is almost 400 meter and the speed is 8 knots. Here in this case the speed is 6 knots, and you can also see the hull system here. Actually in both of the case hull system, all other parameters will be the same. This is the input parameters for LNG tanker vessel. Here you can see that the length of the ship is 266 meter, and hull system parameters has also been changed. And here is the speed here, it is the 6 knot speed here. So you can differentiate among these parameters.
Assalamualaikum and good day to all of you. My name is Haifaa Zira. Today I will proceed on my part on the maneuvering performance in the Suez Canal. In this part, I was analyze the data for the large container ship in the Suez Canal and compare with the LNG carrier. The analysis has been done by considering the ship trajectory path in the canal by bank effect and without bank effect for the tested ship. The larger container ship, which is 399.94 meter, and LNG carrier, which is 266 meter, has been tested in this analysis. And then here is the bank criteria parameter that I was considered in my analysis in the Suez Canal. From the parameter of each vessels, including hull system, propeller, control and rudder parameter, as same in deep and shallow water analysis, I coded the ship trajectory path for the both vessels with constant speed, which is 6 knots. These parts showing the performance of each vessels with different length through the canal. Here is the example of the coding, example of the code that I have coded in this analysis for the ship trajectory in canal. Then from the data, the analysis was done with the same speed to analyze bank-induced sway force and yaw moment towards the performance of vessels in Suez Canal. The sway force repels the ship from the near bank at higher speeds, while the yaw moment repels the bow away from the nearest bank. The closer the ship is to the bank, the larger the sway force and yaw moment experience. Then, the result from the bank effect and without bank effect, as I quoted here, for the yaw moment and sway force, and the result will be discussed later by my teammates in the result section. That showing that it is anticipated that the ship bank effect will have a major impact on the ship's maneuverability and consequently its trajectory. The LNG carrier showing that the original rudder area was adequate to provide the yaw moment required to keep the ship on in intended course from the top to the bottom. This was done without the bank effect. That's all from my part. Thank you.
Good day, everyone. My name is Norsyaqim Iqbal, and I will present the result discussion section of our project and on the maneuvering performance of ships, where we focus on both deep water and shallow water cases. So let's take one example in the slide from deep water simulation, which is case C10 involving the simulation of a large container ship traveling at 8 knots in deep water. So in the turning circle, we can see that the simulation shows us an advance of 2,163.9 meters, which is 5.4 times the ship length. And tactical diameter, which is the second picture, which shows us 2,346.9 meters, or 5.9 times the ship's length. So these values exceed the IMO criteria, indicating potential challenges in sharp turns. So this is the zigzag test, the graph of zigzag test. where the ship demonstrated effective course-keeping ability with a first overshoot angle of 0.43 degree and a second overshoot angle of 0.67 degree, showing a good yaw checking ability even at higher speed. So this is the overall result for all 4 cases in deep water simulation, where we can see the other 3 cases for deep water simulation, which is C11, C20, and C21. So which is in this table shows the red values in the turning circle test indicate the simulation is exceeding the IMO criteria. So this for the shallow water case. It's the same situation for the same container ship at 8 knots. So in the turning circle test, the advanced distance measure was 1325.2 meters, which is corresponds to 3.3 times the ship length. So and uh, wait. And the tactical diameter um, recorded was 1448.0 meters, equivalent to 3.6 times the ship length. Both of these values are within the IMO criteria, which specify a maximum advance of less than 4.5 times the ship length, and a tactical diameter of less than 5 times the ship length. So this indicates that the vessel's maneuverability is significantly better in shallow water, meeting the required standard for safe navigation. So here the zigzag test, we can see the case for 20 degree and 10 degree. So in the zigzag maneuver test in the shallow water, for the 10 degree, rudder angle change. The first overshoot angle was 1.48 degree, which is well within the allowable limit of less than 10 degree for ratio length to velocity under 10 seconds. So this result shows that the container ship maintains good course keeping and maneuverability, which demonstrate efficient yaw checking capabilities with minimal overshoot angles in shallow water condition. The improved performance in shallow water can be attributed to different hydrodynamic conditions, such as increased resistance and altered flow patterns around the hull. Um, so we skip. This is the other cases for the shallow water. So this is the overall result for the simulation from shallow water. We can see and observe that most of C2 cases which involve the LNG carrier in shallow water exceed the IMO criteria for the circle turning test. Thank you.
Okay. Okay, I'll be presenting on the maneuvering performance in the Suez Canal, and from the picture, this is the two picture of the result of ship trajectory in canal for large container ship and LNG ship. Both is at 4.12 millimeter per second, and the graph is Y position versus X position, and we can see from the result that as both ships exhibit good agility through the canal at an 8 knot speed. Next. And this is the result of both vessels approach the bank along the canal sweeping curve. They encounter significant sway force and yaw moment due to the bank effect. And the ship bank effect increases with decreasing ship to bank distance. And for instance, the nearest bank exerts a repulsive pull on the vessels. Next page. Okay, from this graph, we can conclude that the LNG carrier and big container ship bank induced sway force and yaw moments when both were moving at 8 knots, and the LNG carrier and the huge container ship strong peaks of yaw moment and sway force at around 140 and 200 seconds respectively, mark the start of the canal. And it is also illustrates that the longer and narrower LNG carrier has lower magnitude of bank induced sway force and yaw moment than the bigger container ship. And this happen might be because of the massive container ship is larger than the wider LNG carrier, and it is therefore closer to the canal's bank. Okay, next page. This is the result of ship trajectory in canal for larger container ship at 4.12 meter per second with bank effect. And the second picture is on the result ship trajectory in canal for larger container ship at 3.09 with bank effect. And the last picture will be the result of ship trajectory in canal for larger container ship at 4.12 meter per second without bank effect. Next picture. Next slide, sorry. Those results shows that for the larger vessel at reduced speed, the derivative indicate how the vessel's response changes. For instance, larger values of YV, YR, and NV and NR at reduced speed indicate potentially slower response times and increased sluggishness in maneuvering. The next is the maneuverability in the Suez Canal. It shows that lower speeds directly impact the maneuverability of larger vessels, providing more control and time to respond in narrow sections. And the next is how it handles the narrow section, how the vessels handles the narrow sections. When the speeds is reduced, it actually improve handling by allowing for better control, though that might be also cause sluggishness due to the lower hydrodynamic forces on the hull. Next page. Next is on control system parameters. We can see that while the radar's theoretically effectiveness remains constant, real-world maneuvering characteristics change with speed reduction, and it requires vessels to operate to adjust accordingly. And the last part is on the operational considerations. As the vessel's operators must carefully consider the balance between improved control and the increase of sluggishness when navigating at lower speeds in Suez Canal. Next. Okay, I'll be presenting on the conclusion. For the summarize of all the results and the case study, we can conclude that reducing the speed of large vessels, for example, from the 8 knots to the 6 knots, it will significantly enhance the maneuverability, and it will bring with it will result to the acceptable IMO criteria and crucial for effective and safe navigation. And we also can conclude that in shallow water, with higher hydrodynamic resistance, it improves turning performance compared to the deep water. It will aiding compliance with IMO maneuverability standards. Next, we can conclude that in narrow waterways like Suez canals, bank effects such as sway forces and yaw moments, it will intensify with higher speed and closer proximity to banks. It will complicate the vessel to control and increasing the accident risk. The last for the conclusion is implementing adaptive speed control and utilizing advanced simulation tools and real-time data analytics are essentials for safe navigations. Particularly in constrained and busy waterways, and it will improve operational safety and efficiency. Thank you.